knows a lot about the science stuff. Professor Dave explains.
Over the past few tutorials, we have discussed 4 important versions of the CC cross-coupling reaction. We will now conclude with the reaction which actually opened up the entire cross-coupling field, the Kumada reaction. Although it is the first embodiment of the modern cross-coupling reaction, the reaction is seldom used in industry today. The reaction was first reported in 1972 by Japanese chemist Makoto Kumada while working at the Osaka City University. One must also mention the early contributions in this area by French chemist Robert Corrieu. Indeed, the reaction is sometimes called the Kumada-Corrieu cross-coupling. It employs the same types of electrophiles as the other couplings, and as nucleophiles, Grignard reagents are used. The active catalyst is usually nickel-0 or palladium-0, as represented in the general scheme, where M is nickel or palladium. There is much evidence to indicate that nickel catalysis can also involve the nickel-1, nickel-3 cycle, and that transmetallation precedes oxidative addition, especially when the halide and the Grignard reagent are both alkyl groups. Thus, the scheme must be modified as follows. It is known that alkyl halides function as 1-electron acceptors towards nickel-0. This is the activation step. The nickel-1 intermediate then undergoes transmetallation, whereby the Grignard attacks the nickel atom, displacing the halide. The oxidative addition to the nickel-1 species to produce the nickel-3 species occurs from this step, possibly through the intermediacy of a nickel-2 species and an R radical. Finally, reductive elimination occurs to yield the coupled product and the nickel-1 active catalyst. In general, the reaction can be carried out without knowing the mechanism. However, activation of the precatalyst may require special conditions, and one should try both nickel-2 and nickel-0 precatalysts if the mechanism is not fully understood. There are many cases in which only one of the two approaches has worked. We know that the reaction is not stereospecific for alkyl halides and involves radicals as intermediates. The product is often the one where the coupling has taken place from the more open face, regardless of the configuration of the halide. One example is nor-bornyl halides, which yield the exo product only because the Grignard attacks the planar radical intermediate from the more open exo face. The endo face is much more hindered. As Grignard reagents are sensitive to air and moisture, they are not isolated but prepared in situ. Like for organozinc compounds, several methods are available for their preparation. The classical approach involves the direct reaction of magnesium metal turnings with the alkyl or aryl halide. However, Grignard exchange reactions have been popularized by Professor Noschel from the University of Munich in Germany. The procedure consists of treating an aryl halide, usually bromide or iodide, with a THF solution of isopropyl magnesium chloride complexed with LiCl. This triggers an exchange reaction in which the magnesium is transferred onto the aryl group and the halide onto the isopropyl group. The equilibrium greatly favors the aryl Grignard. This can then couple under palladium catalysis to yield a bi-aryl product, as shown in this scheme. Although this procedure is analogous to the Negishi reaction, it operates under milder conditions, often below room temperature. Notice in this case we are operating at -20 degrees Celsius. This procedure also spares reactive functionalities like the nitrile, and is even compatible with esters, as shown here, thanks to the very mild conditions of -78 to -40 degrees Celsius. Thus, the special reactivity of Grignard reagents in transmetallations offers a distinct advantage over other cross-couplings, which may require elevated temperatures. Professor Noschel has developed a complex menu of Grignard reagents, which enable this exchange reaction for a broad array of substrates. They are commonly referred to as turbo-Grignards. This is a specialized topic for practicing organic chemists. One interesting feature of the nickel-catalyzed cross-coupling is the ability to activate groups which are not readily activated by palladium. For example, aryl fluorides couple smoothly. In the first example, the fluoride leaving group is more reactive than the methoxy. However, even aryl ethers, as in the second example, couple under more forcing conditions. All of this is not possible with palladium catalysts. Finally, enantioselective couplings with sp3 hybridized Grignard reagents are possible. Usually, a Grignard is not configurationally stable if the magnesium is positioned at a stereogenic center, and the two enantiomers equilibrate very rapidly. Therefore, a chiral catalyst can direct the stereochemistry by virtue of its ability to stabilize one of the two diastereomeric transition states more than the other, as shown here. Although largely superseded by the Suzuki coupling in most practical applications, the Kumada coupling continues to play a role as an important tool in synthesis, largely due to its extended spectrum of reactivity and the mild conditions involved in its use. The reaction received a boost from Nochel's introduction of turbo-Grignards, making the coupling robust and easy to reproduce. Research in this area is still vigorous. Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.